lot cleaner. Okay, so let's take a look at the matrix form now. Okay, so if you recall in the last lecture, we did something like this. We put 3 neurons. I think we had 3 inputs perhaps, x1, x2, x3, right? All of 3 go over here, so this will be W11, W12, W13, right? So very similarly, these 3 will go over here. W21, W22, W23, and so on, right? So once we created the matrix, once we wrote all the sums, okay, so the S1 equation over here, so there's an S1 after the sigma. Call it S1, S2, S3, right? So S1 will be X1 times W11 plus X2 times W12 plus X3 times W13, and very similarly X1 times W21, X2 times W22 plus W23, and X1 times W31 plus X2 times W32 plus X3 times W33, right? So basically, if you all we are doing is, and of course the biases, plus 1 times V1, 1 times V2, plus 1 times V2. So as we discussed towards the end of the last lecture, this could be easily put in matrix form. Okay, so I can say the matrix S is basically W11, W12, W13, W21, W22, W23, W31, W32, W33, and X1, X2, X3, plus B1, B2, B3. Okay, so then in matrix form, I can simply write Wx plus B. Okay, so that's, as you can see, pretty straightforward to write. Okay, from a computation point of view also, so the way from now on we'll do is, if we create a network, our inputs will be, so these x's are the inputs to the system, right? So this is what we call a vector. A vector is basically n by 1, meaning a single column with as many rows according to the data that's needed, the size of the input, right? So you can see this is also a vector. And of course, this is W is a matrix. So rather than individually computing S1 equal to W11 times X1, W12 times X2, W13 times X3, okay, if somebody gave us a vector, suppose the weights in this matrix are initialized randomly. So our W matrix, suppose in the beginning appears like this. Okay, something like this. Okay, or at some point in time, the W matrix happens to be these values, right? If somebody feeds the data to us, input data, let's say, is 0.1, 0.25, 0.71. So that's the input data. How will we compute S1, S2, S3? As you can see, it is simply one matrix by vector multiplication and one addition. So all you have to do is compute Wx plus B. Okay, and this S will be a vector, or will it be a matrix?
G by 1.
And we call that a vector, right? So this will be basically a 3 by 1. In our example so far, this is 3 by 3, this is 3 by 1, this is 3 by 1. Okay, so the only thing you have to watch out is as you're doing these matrix computations, make sure the dimensions are matching. Okay, otherwise it will cause a problem. Okay, so now I took a case of a very symmetric system. What if I change this such that there's only 2 inputs? And 3 neurons. So 2 inputs and 3 neurons. Okay, so this will be W31 and W32. Okay. So as you can see now, what will happen? This will disappear, correct? Okay. So what will be the size of this matrix then? 3 by 2. Okay, so because it's a 3 by 2 matrix, exactly, that's what I wanted to point out. That now take a look over here. This is 3 by 2. We cannot multiply 3 by 2 to a 3 by 1 matrix.
It will be 2 by 1. Because I have to come. You removed it.
We have 3 neurons, right? So there will be still 3 biases.
F1,
X1, X1 will be 2 inputs.
Oh, this one you mean? No?
X1,
X.
Oh, this one. Okay. Yeah, that will be 2.
1.
So it's. Oh, I see what you're saying. Okay. Yeah. I see what you're saying. Yeah. So this will be 3 by 2. Okay. Is the weight matrix. Okay. So the point I wanted to show you is, even though there's no problem over here, the point I wanted to show you is when we create the W matrix, the W matrix is decided by number of neurons in the next layer, comma, number of neurons in the previous layer. Okay, so for example, let's focus on this part. Okay, we wanted to know what is the size of this matrix, whether it's 3 by 2 or 2 by 3. Okay, so that's what I wanted to indicate. We don't start with, there are 2 inputs, 3 outputs, so we will not create it a 2 by 3 matrix. Instead, we'll start with number of neurons in the next layer. See what's next to it? How many? 3. So this will be 3. So that's the next, that's what I meant by the next layer. Then number of neurons in the previous layer, what's previous to it? So number of neurons or inputs. For the very first layer, it will be the inputs, but from then on, it will be the number of neurons. So this will be 3 by 2 matrix, right? Everybody agree? Okay, now let's go to our example and see if you can clarify all the sizes over here. So let's take a look at it, this example. So now if you can tell me for this part, what will be the size of the weight matrix?
100 times 1,000.
Next, then the first. So 100 times 1,000, right? Then let's go to now this set of W's over here. What will be the size of that matrix? 50 by 100. Okay, and then lastly, this W. Okay, so anyway, so this way our dimensions will match and we won't have a problem. So let's go to this example over here and let's see if you can figure out how it will compute at the matrix level. Okay, in this example, we said there will be 1,000 inputs, right? So for these 1,000 inputs, what will be the size of the x vector? 1,000 by 1. Okay, so now let's go, after we pass it through this layer, right? Remember we have to compute S and we have to compute A, the actual output in each layer. So if I go over here, use a different color. So if I go over here, so my question is, what will be S of 1? Okay, won't that be, so if I call this W1, W2, W3 for right now, okay, so won't that be W1 times X, okay? So let's see if our dimensions match. 100 by 1,000 times 1,000 by 1, correct? So what will it produce then? What will be the size of S?
100
See, when we multiply 100 by 1,000 by 1,000 by 1, right? The answer will be 100 by 1. And you can see there will be 100 S's over here, right? So matrix multiplication is all we need, and of course I forgot the biases, plus B of 1. And this will be, what will be the size of this if we assumed over here were 100 neurons? 100 by 1. Okay, so you can see there's no problem in doing this computation. Okay, so once we have computed the S, correct, then what do we need to do? So if each neuron over here has a sigma, then that's the S, so that's what we just computed. Now we have to pass it through the activation and compute A. So how will we compute A? Suppose it's a sigmoid, right? So as you can see, there are 100 values over here, right? So suppose S of 1 looks like this. We came up with 0.3, 0.28, 1.5, negative 5.2, and so on. So this is our 100 by 1. So my question is, how do I compute A of 1 from these values? If the activation function is a sigmoid, right? As you can see, what's the computation for a sigmoid? So this will be 1 plus e to the minus 0.28. Everybody agrees? Then 1 over e to the minus 1.5, and so on. So this sigmoid that we are going to apply, what I'm trying to say is an element by element operation. To every element in S, we have to apply the sigmoid. Okay. So pretty soon we'll develop the code. So I'll point out to that our code is actually doing an element by element operation like this on this vector. Okay. So requires element by element operation. Okay, so now after we have computed S1, so what will be the size of A of 1 then in this example? 100 by 1, correct? Okay, now let's go to the next layer, and hopefully now you'll see the pattern and it will be pretty easy. So if we go to the next layer then, my question is, how will we compute S of 2? Okay, if you take a look, these are the neurons where this is our layer 2, right? So the input to that is coming from, so first of all, what's the size of this matrix? W of 2?
50 times 100.
50 times 100. So let's write 100.
Times A1 of 1.
So times A of 1. So times A of 1 plus B of 1. Okay, so what's the size of this?
B of 2, which is sigma x y.
B of 1, B of 2, correct. B of 2. Okay. So, is there any problem in computing this? 50 by 1. So what will be the size of S of 2 then? 50 by 1. Okay, so very similarly we'll compute A of 2 by doing an element by element sigmoid on each of the terms over here. So what will be the size of A of 2 then? 50 by 1. Okay, and lastly, let's go to the output now. Once we go to the output, we'll be doing S of 3. Okay, which will be W of 3. What was the size of W of 3? This was W of 3, 10 by 50. Okay, times, what's the input that's feeding to this layer?
50 times 1.
A of 2, which is 50 by 1. And then
B of 3.
B of 3, correct. Which is 10 by 1. Okay, so what will this produce then? 10 by 1, so S of 3 will be 10 by 1, and those are the outputs. Okay, so your next assignment, like I said, will be you'll be creating a capability so that we can create as many layers as we feel like it. We can feed as much data in terms of the vector size as we feel like it, right? All the forward pass, as you can see, will be simply matrix computations, matrix by vector multiplication. So this is matrix by vector multiplication, then simply vector addition, okay? So now let's briefly talk about the backpropagation algorithm. So how will, because we still want to use the delta rule that we developed, but in terms of matrices, what happens to the delta rule? Okay, so let me clean this up a little bit. Okay, so let's go to now the backpropagation. Okay, so anyway, let's pick the same example as before, meaning 1,000 inputs, 100 neurons, 50 neurons, 10 neurons over here. As we did the forward pass, we computed the A of 3 over here. What would be the size of A of 3 once we went through this example? 10 by 1. Okay. So obviously somebody will give us the expected output based on a given data, given X data. So what will be the size of the expected output? 10 by 1. Okay, so our loss will be, or I should say partial L over partial A, will be still the same as before, meaning minus A minus Y. So what will be the size of this loss then?
1 by 1.
10 by 1. Okay, this is 10 by 1. So this is simply a matrix subtraction, as you can see. Then finally we multiply by a minus, or you can do Y minus A. Either way, it's fine, right? So if I now draw over here, here's the loss. Okay, then basically let me 10 neurons over here so that you can easily see. So this 10 neurons basically contribute to the loss. Then let me put 100 neurons over here. Okay, so first thing we want to do is we want to compute delta of 3. Okay, so delta of 3 is basically, as you can see, is the partial L over partial A of 3 multiplied by what? Okay, I erased that picture. What was the previous output over here? Would be A of 2, right? Because this is basically, all of this is A of 2. Because if you take a look at the sum expression over here, right? The sum expression over here, isn't this W2 A2 plus B2? Sorry, B3. Okay, W3. So the sum over here, right, is, so this is sum 3 over here, was the previous, because the weight matrix gets multiplied by this one, and we added to the bias over here. So that was the expression for the sum 3, right? So if we do, for example, now partial S3 over partial A, partial A2. Okay, we are trying to compute the delta, my mistake. Okay, so the delta over here will be partial L over partial times A3, 1 minus A3, my mistake over here. Do you guys agree or no?
Yeah.
So this is the derivative of the activation function, for example, the sigmoid. And this is the partial L over partial 3, which we already have it over here. So this is a 10 by 1. So this is 10 by 1 as we did. This is 10 by 1. This will be 10 by 1. Okay. And then this will be basically a vector of all ones. Okay. So anyway, once we have computed the delta 3, now let's see how will delta 2 be computed. Okay, so first, what will be the size of delta 3 in this example? Remember, delta is the intermediate product of gradients after the sum and before the activation. And so it's basically in the middle of each neuron. So what will be the size of this delta of 3? If there are how many neurons in the output? 10 output. So what will be the size of this? 10 by 1. What will be the size of delta of 2? 100 by 1, right? Because there's one delta value inside each neuron. There are 100 neurons over here. So far, so good? Okay, so now my question is, how is delta 2 related to delta 3? So what is the relationship between delta of 2, which is going to be 100 by 1? Because if you recall, once we have computed the deltas over here, we go back and compute the deltas in the previous layer. So remember, whatever weight is being multiplied over here will give us the deltas over here. So if I do times, what's this weight matrix? What are we calling this? W1, W2, or W3? If this is 10 neurons, 100 neurons, this is W3. So can we do this, W of 3? Let's try to see if the sizes match. Okay, What's the size of delta of 3? 10 by 1. What's the size of W of 3? 10 neurons over here, 100 neurons over here. So what will be the size of this W matrix? We go to the next layer, then the previous layer. Can we multiply these two?
No.
No. So let me give you a hint. There will be some kind of a transpose involved, then this will work. The sizes will match. So how should it be done?
If we transpose delta.
Or let's switch the order. Switch the order as well as do the transpose. So if I did, for example, W of 3 transpose times delta 1 of, sorry, delta of 3. There's no 1 over here. Okay, delta of 3. So now if I put it, it was 10 by 100, right? After I do the transpose, which basically switches rows and columns, what will happen to over here? 100 by 10. And what's the size of this? We already had it 10 by 1, right? So now what will it produce if we multiply the two? 100 by 1. Okay. So what I'm trying to summarize is, as we go back and compute the deltas, we do the W transpose times the delta of the next layer. Okay, otherwise it will not match. So for example, how will I compute the deltas in these 100 neurons? Sorry, we did it. I forgot. Okay, it doesn't match my example over here because in my example, this was supposed to be, after 10 we go to 50. So this should be all 50, and this should be 50. Because our layers were 10, then 50 neurons, then 100 neurons, then 1,000 inputs. Right? Do you guys agree? Okay. So anyway, so it will be 10 by 1, 50 by 1, so this will turn out to be 50 by 1. Okay, so now if you guys can answer me, how will I compute the deltas in these 100 neurons? So prior to this, let's put one more.
The last equation is complete. We didn't multiply it
By the derivative of the activation function. Yes, you're correct. So it should be
8 times something.
2, 1 minus a of 2. Yeah, thank you for noting that. Okay. Because that's the derivative of the activation function, right? Okay, so hopefully if you guys can answer this, then you are in pretty good shape. So let's go work backwards. This is what we are calling W of 2, which connects the 100 neurons to the next layer with 50 neurons. Okay, so this is the layer which we are calling delta of 1. Okay, so sorry, delta with a superscript of 1. Okay, so my question to you is, what is the equation for delta superscript 1? Remember we discussed that we do the transpose of the W matrix first. So what's the transpose of the W matrix? What size will it produce? What was this original size?
50 by 100.
50 by 100. So this will produce 100 by 50 times the delta of this layer. Delta 2, 50 by 1, plus the bias over here, E of 1. And what's the size of biases over here? If we have 100 neurons?
100 by 1.
100 by 1. Okay, so then what will the size of this then? 100 by 1. And of course, I forgot to multiply it further by the there's no bias being added over here, my mistake. We're not computing the sum, we are just, so this then further needs to be multiplied by A1, 1 minus A1. Okay, 2 more minutes, then I'll stop and let you guys go. Now that we have figured out how to compute delta 3, delta 2, delta 1, okay, we need to compute the gradients in the matrix form. So we need, for example, we need delta W of 3, meaning the gradient of W of 3 here. These weights over here. Okay, so remember what we were trying to do was we were trying to compute all gradient in terms of the deltas. Okay, so what's the delta to the, as we are working backwards, what's the delta over here? Delta 3, right? Okay, and if you recall for these gradients, okay, the sum expression comes out to be this. So if we further do partial S over partial A as an example, right? Then it will be the previous, sorry, partial W, it will be the previous output. So this has to be multiplied by the previous output, which is A2 of 2. Sorry, A of 2, not A of 2, A of 2, right? Let's double check, are the sizes matching? What's the size of delta W of 3? It will be the same as the weight matrix, which will be, sorry, I'm over here. Here is 10 by 50. Okay, what's the size of delta 3?
1 by 1.
10 by 1. What's the size of A of 2? 50 by 1. So does this match? So what should we do? A2 transpose. Okay. So do the transpose over here, then this will become 1 by 50, and then you can see will give us 10 by 50, right? Very similarly, can you tell me what is delta W of 2? There will be delta of 2 times the previous output, A1 transpose, right? What about delta W of 1? Delta of 1, what's the previous output? X, exactly. X transpose. Okay, you can verify what should be the size of delta W of 1. So these are the